Now we can finally discuss the last theorem of the course, which is Gauss's theorem, or sometimes called also the divergence theorem. And this is a theorem that allows you to compute the flux in a different way. So now imagine, here's what you should have in mind. Imagine you have a surface S which encloses some volumetric region V, or R, maybe for region. So the interior of this surface, the inside of this surface is what I'm calling R. And so if you have a vector field F, the divergence theorem allows you to compute the flux along S in terms of a triple integral involving R. So let's write divergence theorem here. So the idea again is that if S encloses some region R, then the triple integral, or the flux along this surface, which remember was the dot product between F and N, here's N, equals a triple integral over this region of what's called the divergence of F, where so this symbol represents a quantity called the divergence. There's a scalar field which is this one, and here F equals F1, F2, F3, and again the point is that if you think of this as almost like a dot product, this nabla, or this triangle, is the partial with respect to x, the partial with respect to y, the partial with respect to z. So at the end of the video, I'll show you an animation that explains a little bit what the meaning of the divergence is. But the idea is that at a point, the divergence measures whether some net fluid is being created or destroyed. And that makes sense because then you're saying that the stuff that manages to escape the surface is related with how much production of material is happening, production or destruction of material is happening on the inside of the surface. Okay, so the proof of, I won't do the proof of the divergence theorem, is in a sense it's also like a analog, a generalization of Green's theorem. So there's like a version of Green's theorem for the normal component of the vector field, which is called the normal version of Green's theorem, which I'll skip, so you don't need to worry about that one directly. And then this normal version of Green's theorem would have been proven in the same way in which I proved the version with the tangent component, which was related to work. So you would do like a Taylor approximation to figure out that what you would expect to see in the integral is something that involves the divergence. And so what I want to do now, before showing you this animation, is simply do some examples for vector fields. Divergence is way easier to compute than the curl because it's just a scalar quantity. So let's just say, for example, that your say if your vector field is f, which is this, then the divergence of f is just a partial with respect to x of the first component plus a partial with respect to y of the second component plus a partial with respect to z of the third component. And so that gives you 2x plus 3x plus 3c squared. Okay? And in general, I mean, it's just applying a formula. If you want me to mention this briefly, so you should just say, this is a useful remark. So this is a scalar field. So that is, it gives a number at each point in space. Right, because this depends on the point in space you're using. I guess this is really 5x plus 3c squared. And so if the divergence is positive, so if the divergence of f is positive at some point, then you call this point a source. If the divergence of f is negative at some point, you call that point a sink. And again, that you should think that literally at that point there's some fluid being produced. At this point there's some fluid being destroyed. And if the field happens to be always with divergence 0, these three lines just means that it's always 0. Then the field is called solenoidal. And that's like, there are fields that have this property. So like one of Maxwell's equations, for example, is that the divergence of the magnetic field is always 0. And so that means that there's no field on the net, there's nothing that works as a magnetic charge in the same way in which a proton is a source of positive, it's a positively electrically charged particle with positive charge. So a proton is actually a source of the electric field, and an electron is a sink of the electric field. But for magnetic fields, there's no like analog of protons or electrons. So that means that there's nothing that's like producing on its own magnetic field, which is why when you have like a magnet and you cut it in half, then you cannot isolate the north and south poles. You sort of get two on each piece. You get a new north pole and a new south pole, because if you look at the field lines of the magnetic field, they will be closed loops in this case. So in the next video, I'll do an example with using the divergence theorem for computing flux, and then I'll show you right now this animation. Now I will show you the interpretation of the divergence and the curl of a vector field. So suppose that we're considering vector fields on the plane. Say for example a vector field whose components are x and y. And so here's a representation of the vector field. Notice that this vector field happens to agree with the position vector of a particle. So the arrows are just radial arrows pointing away from the origin, as you can see here. And it's a quick computation that in this case the divergence is 2 and the curl is 0, in the sense that it vanishes identically. So what that means is that the divergence being 2 means that at each point there's some sort of creation of fluid, or fluid is escape. If you put like a small region here, fluid is there's a positive flux going through this region. Let's see. So this is an animation. So you think of each point as being a source of fluid. On the other hand, the fact that the curl is 0 means that in this fluid, if you put like tiny paddle wheels along in space, they won't move because there's no net rotation of the fluid. On the other hand, we can go to well, and since the curl is 0, also that means that when you compute the work along some closed curve, the work has to be 0, as we had already seen before. But obviously, depending on other curves which are not closed, the work may still not be 0. Now we can change vector fields. Let's see. Let's try to find. Okay, so in this vector field, let's okay. I think this vector field is now has the first component is negative y, the second component is 0. So in this case, you check that the divergence is 0. So yeah, meaning that there's no net fluid being produced at each point. While on the other hand, the curl is no longer 0, it's 1. And so that means that if you put tiny paddle wheels at each point, they will start rotating. And then you could have something, let's see, more interesting, that I think there are a couple of examples here. Okay, this is cool. This one depends. Now the first component of the vector field is this expression. The second component is this expression. It's way more complicated vector field. And so you see that both the divergence and the curl depend on the point. So as you move, so here, points with negative divergence, they're like sinks, meaning that mass is being destroyed or absorbed into this point. Points with positive divergence are sources, as I was saying. And then again, if you put little paddle wheels, the curl will measure the rotation of the paddle wheel in the, and whether if the curl is negative or positive, that tells you if the rotation of the paddle wheel is clockwise or counterclockwise. And that way you can see that there's a lot of interesting things going on for this particular vector field, given that they depend on the everything depends on the point that you are considering.